This is the second and final section of Chapter 8, Decision Analysis, and this section is all about utility. So to understand utility, we first need to remind ourselves about the expected monetary value, or the EMV. Now, when we calculate the EMV from a decision tree, it gives us the expected payout, but not the risk involved in getting that payout. So here's an example here of where the EMV may not necessarily be useful. So let's say we're expecting 100 people to pay £5 to enter a competition. So you've got an income of £500 and the price for winning is £200, and that £200 is going to come from your income. And let's say that if someone wins the prize after only 5 people have paid £5 to enter this competition, so you've actually only had an income of £25 and then you've got to pay £200 out, you've actually made a loss of £175, so then you would have actually made a loss. So even if the EMV were positive, the risk of making a loss could be quite high. So to avoid this problem, we can use a different measure called utility. And we use this to calculate, or which we use to calculate the expected utility EU. Just like we calculate the expected monetary value, we calculate this expected utility, where U is a function of the profit X. So U of X is going to be some function of X, and from that we will calculate the expected utility, and that is going to be a measure of the risk in taking a particular decision. Now this function of X here may or may not contain a variable called R. This value of R is always greater than 0. Example 5. A school has to decide whether to offer a dice game described on pages 252 to 253. And I'm going to read out what that dice game is. So you're the head of maths at a school that is trying to raise some much needed money by holding a summer fete. You are asked to devise a game that will attract a lot of interest and raise a significant amount of money. You propose running a dice game in which 6 dice are thrown. The charge will be £1 for each attempt, and the prize money will be offered will be £2,000 for obtaining 6 sixes in a single throw. You expect that there will be 400 attempts during the day. So for a payoff of X pounds, the school determines that its utility function is U of X is equal to 1 minus e to the power X over R. And what we need to do is to calculate the school's expected utility, given that first of all R is 400, then R is 200, and then in each case interpret the results. So the first thing we need to do is to draw a decision tree based on this dice game that's given here. So first of all, you can decide whether to offer this game or not offer the game. If you don't offer the game, there will be no payout. And if we do decide to offer the game, then somebody could claim the prize or somebody may not claim the prize. Now, if nobody claims the prize, you'll have a payout or payoff of £400 because you'll get £1 from each of the 400 people that have attempted this game during the day. And if somebody does claim the £2,000 during the day, well, you would have got an income of 400. You would have had to then pay out, and you would lose. Your payoff would be negative £1,600. So now we need to work out the probability of winning and losing. So the probability of winning means that you're going to get 6 sixes in a row like this. So 1 6 times 1 6, 6 times, which is going to be the same as 1 6 to the power 6. So we'll work that out. So 1 6 to the power 6. And if we do that on our calculator, we get 1 over, let's have a look, so it's 46656. Then the probability of not winning, well, that's just 1 minus the probability that you win. So 1 minus the number above, and that will be 46655 over 46656. Now we need to work out the probability that somebody claims a prize and the probability that someone doesn't claim a prize. Now actually the probability that someone doesn't claim a prize is easier to do, because it basically means that 400 people don't win. So that would be 46655 over 46656 to the power of 400. So what we've got here is 400 people not winning. And then the probability that someone claims a prize is going to be 1 minus this. Now this is easier to work out, because the probability that someone claims a prize, well, there are lots of options. It could be the first person that claims the prize, or the second, or the third, all the way to the 400th. It's probably going to be easier to use binomial to work that out. Even easier, work this out. No one claims a prize. All the people, all 400 don't win. And then the probability of claiming a prize is just going to be 1 minus that. So it'll be 1 minus 46655 over 46656 to the power of 400. Okay, so let's work these out. They're probably going to be decimals, I think. So I've worked out the second one first, and that gives me a probability or a value of 0.99146. and then there's a 1 after that, and then all I need to do is just 1 minus that, and that gives me quite a small probability here, so 0.0085368 and so on. So these will be the probabilities that go on the branches. I haven't got a lot of space, so let's just color code it. So probability claims a prize, that's going to be this probability here, the 0.008561, and let's use maybe green. Hopefully you can see that there. So the probability on that branch is going to be this 0.991463 number. Okay, so now we can work out the utility, and remember its profit is going to be X, or the expected payout will be X, and in part A here we're using a value of 400. So U of X, so that's going to be U of negative 1600, is going to be equal to, it's 1 minus E to the negative X, which is negative 1600 over R, and for this it's 400. And that gives me a utility value which I can put up here as negative 53.59815. And now I just replace the numbers for X. So I'm working out utility for the 400. So the negative 1600 now becomes 400. So U of 400. That means that the negative 1600 at the top of the fraction now becomes 400. And that gives me a value of 0.63212, and there's a 0 after that. And then I also need to work out the utility here. So U of 0, that's going to be this calculation. Anything to the power of 0 is 1, so 1 minus 1, that doesn't change that value, so it's going to be 0. So now I'm in a position where I can work out the expected utility. That's what's going to go in this circle here. And that expected utility is going to be this utility value here. So negative 53.59815 times by its probability, which is this one here, the 0.0085368 number, and then plus this utility value 0.63212 times by its probability, which is the 0.991643 number, and that gives us a value of 0.169, and that's to 3 significant figures. I think 3 significant figures should be enough for that. So that's our value for part A. We'll work out part B and then we'll interpret both the results. The only difference with part B is that because our value of R is different, these utility values will be different. So let's work those out first. So the first value we're going to work out with this expected payout, but now with a value of R here of 200, and that gives us a utility, quite a low value actually, of negative 2,979.957987. And now changing the payoff or profit value to the 400 we have at the bottom here, that will give us a utility of 0.864647 and so on. Now the calculation for the expected utility is down here, so it's the same thing, the utility times by the probability. So same probabilities as before. To three significant figures, this gives me an expected utility of negative 24.6, again to three significant figures. So let's now interpret these results that we've got. So in part A, where we had a value of our 400, this is given a value of expected utility of 0.169 utils. We can just state the number, but you might call it utils. So the school should take the risk and offer the game. So for part B, the value of R equal to 200 has given a value of negative 24.6 to three significant figures utils. So the school should not take the risk by offering a game. A negative value, a much higher risk than this positive value here. Example 6. A company can choose one of three business options A, B or C. The profits in pounds associated with each outcome are shown on the decision tree below. So here it is. Part A. Using the decision tree, calculate the optimal EMV to determine the best choice. Okay, so let's do that. So very straightforward. 750 times by 0.7 minus 550. So this is for the first one, times by 0.3. That gives 360 here. And then 400 times by 0.7 minus 200 times by 0.3. And that gives us a value of 220. And then last one at the bottom, 500 times by 0.7 minus 300 times by 0.3, and that gives us a value of 260. So based on this, the company should choose option A, this one here, as this has the optimal EMV, expected monetary value of 360. So on next part of the question, for a profit of X pounds, the company's utility is given by the square root of X plus 600. Part B, using expected utility as the criterion, determine the optimal choice. So I'm going to work out the utils and put them over here. So I'm going to have, for the first one, X is 750. So I'm working out the square root of 750 plus 600. I'll write down all the values in a moment. Second one, that will be the square root of negative 550 plus 600, and so on. 400 plus 600, negative 200 plus 600, the square root of that, and 500 plus 600, and then negative 300 plus 600. So if I work out each one of those on a calculator and give the answers to three significant figures, for the first one I'll get 36.7, for the second 7.07, and so on. So I'll now work out the expected utility by multiplying each utility by the probability and then summing them together. So doing that for the first one, 36.7 times by 0.7 plus 7.07 times by 0.3, 27.8. Doing a similar calculation for the second one, 28.1, And then the last one, same type of calculation, will give me an expected utility of 28.4. So based on expected utility, the company should choose option C. It's got the highest one here, as this is the optimal expected utility at 28.4, higher than options A and B. Example 7. Tim is considering whether to play a card game. If he picks Jack, Queen or King at random from a standard pack of playing cards, then he wins a prize. If he picks any other card, then he loses £5. So part A, draw a decision tree and state Tim's best course of action using the EMV criterion, given that the prize on offer is £12. So let's draw our decision tree here. So his decision will be either that he can play or not play. So obviously if he doesn't play, then his expected or his payoff is 0. If he does play, he's either going to win or lose. So let's put that in. So win here, lose here. And if he wins, he will win £12. And if he loses, he's going to lose £5. We need to work out the probability that Tim will win. Now he's going to win if he gets a Jack, Queen or a King in a standard pack of cards. Now there's going to be 12 of those out of 52. So that is 6 over 26, which is 3 over 13. So he's got a 3 out of 13 chance that he's going to win, which means that he's got a 10 over 13 chance that he's going to lose. Let's work out his EMV, expected monetary value, and that'll be 12 times by 3 over 13 minus 5 times by 10 over 13. And doing it on the calculator, we get negative 14 over 13. So we get a negative EMV, so minus 14 over 13. So since this EMV is negative 14 over 13, then Tim's optimal strategy is not to play. So what we would do is we would put a couple of lines across here and cross out the non-optimal strategy. Tim only has £5. He uses utility is equal to cube root of money squared to reflect his risk aversion. Part B, calculate the minimum prize amount that would make it worthwhile for Tim to play the game. So first of all, I've drawn the decision tree. It's going to be the same as the previous one, same probabilities, and I'm going to use X to stand for the prize amount. And what I'm going to be doing is write some equations, solving for X to work out what this prize money needs to be, or the minimum prize money needs to be. So let's work out what these values are going to be here. So he's got £5. So if he doesn't play, he doesn't win or he doesn't lose, but it's not about his winnings. It's about how much money he's got in his pocket. He keeps the £5. So we're going to put £5 here. If he does decide to play and he loses the £5. He doesn't gain anything. So actually, this amount here is going to be 0. He's down now to £0. So this route here, he keeps the £5 in his pocket. If we get to this route here, he hasn't got the £5 in his pocket. He's got £0. So you actually need to think about how much money does he actually physically have on him for these values, and for these we'll now, once we've got the last one here, we can then work out the utility. Now if Tim plays and wins, well, he gets this prize of X pounds, and he keeps the £5 that he had in his pocket, so he's not going to lose. So he physically has this money here in his pocket, because this is not a game where you have to play to enter. You try it out, and if you win, you get the prize money. He still has the original £5 in his pocket. If he plays and he loses, that £5 is now gone. So as I said before, think about this as the actual money that he has in his pocket. So now we'll put the utilities in. So for x plus 5, the utility will be the cube root of this money squared, so x plus 5 all squared. For 0, that'll be the cube root of 0 squared, which is just going to be 0. And for not playing, keep the original £5 in his pocket, will be the cube root of 5 squared, which will be the cube root of 25. Now, if Tim is going to play and it needs to be worth his while, then what we want is that the expected utility of playing, so the expected utility of playing needs to be greater than the expected utility of not playing. And we can use this to find x. So expected utility of not playing. I could have used a tilde symbol. Let's work out what it is. So the expected utility of playing, well, that's going to be this cube root of x plus 5 all squared times by 3 over 13 plus 0 times by 10 over 13. That's just going to be 0. And that needs to be greater than the expected utility of not playing. Well, that's just going to be the cube root of 25. So cube root, not square root, cube root 25. So we want to solve this for x. So the first thing that I would do, so we know that this is 0, so we can forget about this part here. Yeah, the first thing that I would do is to cube both sides, get rid of square root. So for our cube root, if I cube both sides, I get x plus 5 squared times by 3 over 13 cubed, which would be 27 over 2197 is greater than 25. Continue to solve for x. So we'll have x plus 5 squared is going to be greater than, and it's going to be 25 divided by this 27 over 2197. And if we do that, what we'll get is 54925 divided by 27 over 27. Then we'll square root both sides, just put this here, and that will be x plus 5 would be greater than, now if we square root this fraction here, it actually ends up as being 65 root 39 over 9. And then if we then take away 5 from both sides, we'll end up with x is greater than, now we get some long fraction thingy, it's like negative 45 plus 65 root 39 over 9. Won't bother with that, let's change it straight to decimal. So x needs to be greater than 40.1027 and so on. So this is the prize amount. So the prize amount needs to be at least this. In other words, the prize amount needs to be at least £40 and 10 pence to make it worthwhile for Tim to play. So I've just put that sentence down. The prize money needs to be at least £40 and 10 pence to make it worthwhile for Tim to play, based on the utility that he has. Any less than that, then we would have a negative utility. We want it to be positive. We want the utility of him winning greater than utility of him losing or not playing. So you should now be able to do exercise 8b, which you'll find on pages 257 to 259 of the textbook.